Okay, now in pre-calculus. That wasn't pre-calculus. This was two courses before pre-calculus, which is intermediate algebra. Somebody just came to this area from the place that had a much better education system. Okay. Hear that, or, in your chapter two, learn everything from the town. Okay, well, question mark, what's the domain and range of this function? Square root of 3x plus 12. Well, we know that where it's only defined for positive and non-negative numbers. So 3x plus 12 has to be greater than or equal to 0x greater than negative 1. There's your domain. Okay. Well, there's your domain. What about the range? Range is a little more rigorous. Where everything has to be greater or equal to 0. It has to be greater than or equal to 0. So you know that the domain or the range doesn't include any negative. That's yeah. So 3x plus 12 can take any positive value. Then the square root can take any positive value. It's not a rigorous statement. You'd have to prove that. But we pretty much know that it's true. So you got to know the rigor lies and how to do things rigorously so that you don't do ignorant things. Okay. So intuitively we know this. And we can make it a little tighter. We could graph 3x plus 12. Well, it's a straight line with the 0 at x equals negative 1, a positive slope. It goes everywhere, takes any positive value. Now, if you accept it, if the thing you're taking the square root of can take any positive value, does that mean that the square root can make any positive value? Prove that? So most people can prove because your calculus courses are taught at 2 level. So that, and I keep saying, you your second year engineering, whatever college engineering, you're doing all right. Or, you know, anything from all right to really well. Depending on the day and which one of these. Okay. Can you prove that? Can you think at that level? Something maybe not, maybe everybody can, and you nobody can. How do you prove that? Well, actually prove that at the end. Okay, it's very simple. Y equals square root of x, right? We can solve that for x. X equals y squared. That means for any y, you just square it, and you can get that y, no matter how. Okay, but you see that argument? I'm not sure. Okay, so anyhow. Now we can do this. We take this function and solve for x. Okay, when similar thing happened, we don't get x equals y squared like we would if we just did y equals square root of x. We get x equals y squared minus 12 over 3. And for any y, then there's an x that solves the equation. Okay. Because right there it is. And that number has to be greater or equal to negative 4 because y has to be greater than or equal to 0. And you write that out rigorously, not that anybody learns to write out anything rigorously at the pre-calculus level. Good. But kind of know how to do that. Well, then it gets kind of neat. The graph. Here's a simple graph. There's the table for x squared, negative 2 to 2. Okay, you switch columns and you get the square root. Except you got to discard this part of the graph. The square root can't be negative. Okay, meaning you got to kind of discard this part of this graph, but there you have it. And then you can easily, yes. Probably right here. Yes, that first table, you get this. These are the values that we discard because they're not going to result in values of the square root. And the force function has to be single value. If we included those numbers in the table, the function wouldn't be single value. We have two different values for given x. So anyhow, we construct the graph. So there's our graph. There's a graph of this function. That's an inverse function. That reversal in the table is how we construct the inverse function. Take that inverse function, do a little arithmetic, and factor out the square root of 3 times x plus 4. Now we know we have a vertical stretch y to the square root of x plus 4 by the factor square root of 3, which is about 1.7. And then this is the horizontal shift 4 units of the square root of x function. So we do that. It looks like this. The x function. The y value for any x value can be represented by an arrow. We add on an arrow 7/10 that long. We get 1.7 times the y value. And we do that for just 4 points. And we get 4 points that we can connect with a nice curve. And we got a vertical stretch of this function. And then we shift the 4 units left, and we got the thing. And look there, we see our domains in the graph. Multiple ways of getting domains, multiple ways of analyzing the problem. This is something that's simple enough to grasp immediately. For somebody to level. And like intermediate algebra students thought that was really cool. And then there's a little more we can do, ultimately. Because the domain of square root of x is 0 infinity. And that's so because no matter how big x is, y to the square root of x means y squared equals x. So we know it's kind of x does it. So I don't think I finished my sentence here. The overall because of that, the range of this is also 0 infinity. So there's that, then able to put arrow in these. So I thought that was a kind of neat bunch of connections that I was actually able to make with an intermediate algebra student. It's going to be real well figured out. One free college student taking conventional computer, or will bother the grasp. Most one could. But due to lack of background, interest, time, was what. Meaning, if the course gets taught in such a way that even people who are working at a pretty rigorous level here, which is what you all miss things in that course. And there are connections you never make. For example, you understand that why the derivative of a constant multiple is a constant multiple of the derivative. It's a vertical expression. What happens to slopes here? If I multiply all these numbers by 1.7, all the slopes are multiplied by 1.7. There it is. Constant multiple rule. Okay. And it can be done that way. It doesn't get done that way. It's done by, it's a somewhat more rigorous argument, which is great, but it's good to understand that. Okay. It helps with visualization, especially the kind of stuff we're trying to talk about in this course and in multivariable calculus. And pretty much for the rest of the semester. Okay, now we have this picture last time. What we're talking about is magnetic field due to the current in this segment at a point P. Oh, well. enlarge this segment. Here is your, well, the L vector. Here's the snap point. Call it X bar. And this current is running along. It's going to be X. And the point P is that coordinate X Y. We want to know the magnetic field that results in this current at this point. So that wait a minute. Goes on. What's this? Now let me take that out with my right hand. Okay, so if I delta L cross R would be out of the board. If this is the current, put your thumb in the direction of the current, your fingers curl around the axis in the direction of the field, and that's consistent with I cross or the delta L, I delta L cross R. Okay. You understand that? All right. I'll have is your unit vector in the direction of R. Okay. Well, that's magnetism. Well, there's things that we can do. So everybody see that little piece of blue chalk there? Okay. And you point in the direction that blue chalk is. Okay. What's the direction of that piece of blue chalk? Can you see it? Okay. Probably toward the from here. It's kind of aimed at the back corner of the room. Okay. So it looks like, 20 feet that way, 10 feet that way. Really look like that. If I get in the right position, maybe I can make myself. Okay, something like that. Okay, it's in that direction. Now you hear that light there making noise. Started now. Bothered me for a while, but I've gotten used to it. Hopefully it didn't bother me too much. So I want to know if you have a current running in a wire. Okay, maybe it's a long, infinitely long wire in this direction. And you just interested in the contribution of the current in this segment. The magnetic field at the center of that light. Okay. So think about what would the direction of the field at that point be? Field just due to this little cycle. Okay, we got blue there. Focus the camera. Hopefully it's all right. Okay, so well, fingers in the direction of I delta L. That's whatever your cross product is, your fingers go in this direction, and you got to turn toward this direction. So you really want to get used to that. Especially if you're going to do anything like this. Okay. In your engineering. What's the transfer? And of course, you're going to be in it in about 4 or 5 months. Okay. Make sure nothing happens to your right hand. Okay, well, fingers go in the direction of the current, which is that one, right? Now you orient your hand any way you can. I can't quite get 360 degrees there. You get 360 degrees. Pretty close, yeah. So it's kind of a stretch. Maybe if I took up stretch, you're gonna find start stretching something that gets more flexible. Yeah, and stretch it more. Okay, well, anyhow. Okay, so here we go. Now, if the light was directly above me, I'd have to have my hand like this, right? But it's not. And if the light was straight over that way, I'd have to have my hand like this. And if the light was over there, I'd be in trouble. Okay. But the light's about there. So now I turn my hand about like this, and there it is. Okay, everybody eventually got there. But you want to get that instant. I mean, maybe not instant. I don't think the instant. Okay. But I don't think about this before that much. If you think about it, keep thinking about it. It becomes second nature. It's quick. It's not something you want to get hung up on. And of course, about electromagnetic fields. Okay. We're doing some electromagnetic fields here. Actually, by the end of the semester with this monocle calculus, we can just do this. I'll let you get that. Okay. Okay, so man, we've got that now. Gonna think about what would be if this was what we have, if this was a segment of a circle. Okay, a circle in the plane parallel to the floor, horizontal plane. And that point up there being a point on a vertical axis through the center of the circle. Okay, that's what we want to really get to. So it's like, okay, here we go. Here we are, and that's why. Here's a point. Maybe this little piece of chalk. Defines a small segment of the circle. So we've just decided that my R vector is here, and my I delta L vector. Oh, sorry. Okay, I'm thinking about two things at once. I really want to do the point at the center of the circle before I do this one. That's not what I was talking about. Before we actually do this, I'm just going to start to look at the picture. Here's my I delta L, and my R vector was here, and my I delta L vector, and this is just my delta L. My I delta L vector is here. Okay. And then when I do the cross product, it makes a certain amount of sense. That corresponds to the current in this direction. I've got to turn my hand so that I can turn this vector into this one. Okay. Also, it should be obvious from the geometry of this thing, its vectors are perpendicular. Okay. Because the radial vector from here to here is perpendicular to this, it's tangent to the circle. And the whole plane above that radial vector is therefore perpendicular to this, and this thing's in that plane. Okay, that makes sense? It's three-dimensional visualization, that thing that I was totally unable to do. It was a complicated situation, the way it had the board. But no excuses. Just wasn't there that day. But anyhow, you get that. So what's the direction of your field contribution? Well, okay. What angle does this make with the z-axis? What are the components of v parallel and perpendicular to the z-axis? Well, we'll get to that. Let's back off just for a little bit and just do the circle. Let's just do the circle and the point at the center of the circle. That's really easy. And once you've done that, okay, you just have to look at those components and then take the final movie. So here we can place it. Here we have it. Represents a circle. Here's a circle. Okay. So now we want to get the contribution of an arbitrary point of the current and an arbitrary segment. We want to get the field at the center. Okay. So now if this thing is in a horizontal circle, and the center of the circle is in the plane of the circle, directly below the center of that light fixture, right about there. Okay. What's the direction of the field contribution to the field at the center of the segment? Okay, so this is a much simpler picture. I think everybody got it. Like your R vector here. I delta L is here. So I delta L cross R, no. Here's your delta L. Okay. So there's a nice symmetry argument, very easy to make. It tells you what the total field is. But I'm going to do more formal. Okay. Yeah, I noticed people are still having trouble partitioning it. I'm going from the partition to the sum to the end. Okay. And again, I think that all goes back to pre-calculus before. Didn't get the rigor through calculus. The rigor really didn't fall together in your calculus portion. Okay. It didn't my calculus portion. Okay. So I had the calculus. Okay. But it kind of woke me up with it. Managed to develop about halfway through my software. Okay. So you know, every point we need. So this is your typical interval. And so for typical in implicit, we've got a current I running in this. Never actually said that. For typical I delta L, what I mean by typical I delta L. That's a question mark. First of all, we have to parameterize the circle. Let it parameterize the circle. There's a very convenient parameterization. Okay. Another convenient parameterization, we cosine of 2 pi t, sine of 2 pi t, t from 0 to 1. Okay. Put it, I don't make a note. And that's often really convenient because it's easier to integrate from 0 to 1 than it is to integrate from 0 to 2 pi. But it's not difficult either way. It's a choice, and it's a choice of taste. Would you rather have a complication of 2 pi, in which case you might have to use the chain rule to take the derivative? Or would you rather have a nice interval that goes from 0 to 1? Makes no difference at all. Just whatever your taste, whatever you want to, whatever you want to do. I'm going to go ahead and use the derivative of 2 pi. Okay. Okay. What's the first thing you do? You parameterize your you partition your parameter. Okay. You got your partition. What do you do with that? Well, you set up the typical interval. You throw your TI star in there. Okay. And now your I delta L will be your I delta T sub I. Okay. But it's a vector. And it's a vector in what direction? Well, the derivative of the cosine is the negative sine, the derivative sine is the cosine. So it's in the direction of this. Okay. Now you can do that just by taking the derivative. Okay. It's the derivative of your R vector, which gives you a tangent vector. Okay. You can also do it geometrically. You can that'll be swap it down up here. You can say if this is your. Yeah, there's your R vector, okay. Your tangent vector has to have a direction. So that's something, right? It has radius A. Okay. So this would be. And over here you have an A. Over here you have an A. Right. In any case, the direction is the direction of cosine Ti star R plus sine of Ti star J. You're going around counterclockwise. This vector is going to be orthogonal to this vector, which means it's going to have, like you're going to have a negative reciprocal slope, which is exactly what you get when you do this. Right? You just take your x and y coordinates, reverse them, and make one of them negative. Well, if you're going to go counterclockwise, then have to make the sign in front of the I vector. Okay. So all I'm saying is you can reason it out this way just by negative reciprocal. But in a more general curve, you're going to have to take a derivative of this vector and make a unit vector out of it. I've already made a unit vector out of it. You take the derivative of that, and then you divide by the magnitude, which is A. This is what you get. Okay. And everybody got to do that multivariable calculus stuff. But it's still a legal operation in this course. It's done without multivariable calculus. Okay, so there's your vector. So your delta V sub I is this. And then that's an easy calculation. So let me just stop there. Ask you to calculate, but of course. Okay. And then it's over R squared. And it's on R hat. Okay, I started it for you. Gonna get long. Use a little bit more boards. Okay, cross with something. Divided by R squared, right? So what's the cross with? And we can say above all. Okay. See what you get. Okay, I'm doing pretty well. Somebody got it, so we almost had it. Maybe this 132. So first, your I delta L is this for the reason I went on. Okay, And you can do that using your whatever calculus, you do it, and it's, so we've established that your R factor. Right now, compare it with. Your R. And again, you take the derivative of this and divide by the magnitude of the derivative and get things. Do it geometrically. Perpendicular nature of the tangent, perpendicular slope, or whatever you want to think about, and you get it that way too. R hat. Is just this because magnitude of R is just a times the cosine squared. Which is one. So when you divide by R being the magnitude of the R vector, that's the thing. Because of the magnitude of R being equal to A, that's what your little R stands for in the formula. And so down to just crossing this with R hat, which is I will have to get this board. But then, of course, R is just A. So we can do that at this point. We don't have to. So this comes out pretty simple. I cross I is 0, right? And J cross J is 0. And there are only 4 terms involved in this cross product, and it's 2 of them that are both 0. Okay. And then the negative, well, I cross J, I cross J is K. We have a negative sign times a sign. Okay. The negative sign squared Ti star. And J cross I is negative K. So that gives me a negative cosine squared. So this is just one. Well, so we find that this is very simple. Now we could have figured that out using just the original diagram. Throwing it into the whole formula, because sometimes you need to do that. The delta VI is the sum of your K prime I delta Ti over A squared, right? So how are you gonna do with that sum? Well, K prime I and A squared are constants. It's a sum of terms, all that have same coefficient. So that's just add up your delta TIs. What do you get up when you, what do you get when you add up your delta TIs? Now, that's really what it comes down to, so let's just go back up here to our partition. What do you get up? What do you get when you add all the delta TIs? It's actually not. Okay. Well, I kind of wrote down a hint here. Okay, you start this, you know, what's I equals 1, you get T1 minus T0. If I equals 2, you get T2 minus T1. If I equals 3, you get T3 minus T2. And it just keeps going, I could complete it. It should be obvious what's happening. Got a minus T0 here. This T1 is canceled on this one. You got T1 minus T1, you got a T2 minus T2. Okay. And you're gonna have a T4 minus T3, so you're gonna have a negative T3 to go with this T3. Well, that's gonna happen all the way to the end. At the end here, your Tn minus 1, it's obliterated by this one. Okay. Your Tn minus 2 will obliterate Tn minus 2 in the previous term. And all you're gonna be left with is a T naught here and a Tn here. So it all comes out, you don't even have to do an integral. Okay, something's not right there. I'm not comfortable with that square. I can consult with the book. And they never have. Think about. I think the text will run you through this. Let me do it geometrically. But what I'm gonna do is I'm gonna divide this up into bunch of equal spaced increments, each of which are modeled by a straight line. So that got an I delta L here. Let's say in this direction. And then over here I have another I delta L opposite this one. It's measured with respect to the order. Don't really need the opposite one. There it is. Okay. And the delta B. Let's yeah. If I did this, something would become on it. What did I do wrong here? Your I delta L is not I delta T sub I. The current time to length is not the same as the current times time interval, right? Or a parameter interval. This parameter doesn't have units of length. A delta T sub I. Right? It's a length. Delta T sub I is going to be the same for a small circle as it is for a big circle. In the big circle, the length interval is clearly bigger. Okay, so I just don't have overlooked that. And then started accepting it. So got to put an A in here. And of course, the A here and the A here result in an A in the denominator. Right along about here, I said, whoa. It can't be an A squared. Did not identify step until I did this. Now, we go back to what I did at the beginning. A lot of different ways that you see that. Well, you can see the domain of that square root function. Pre-calculus, early pre-calculus idea. It's kind of a revelation if you think about it, how you can do it algebraically, geometrically, in many different ways, at least 3 different ways to understand that domain. Even though you can get it, you can remember how to do the algebra. You really understand it deeply. You can always understand things more deeply. So it's like you look at something in at least 2 different ways. It's like having binocular vision as opposed to monocular vision. Okay. You get some depth perception. So just doing this geometric picture showed me immediately what was going on as soon as I considered this, because the delta L is and I parameterized it originally with delta T. I use the same delta theta all the way around. And we can parameterize in terms of theta from 0 to 2pi, just like T from 0 to 2pi. There's our geometric meaning. We have K prime times I times A delta theta over A squared. And of course, the delta L is A delta theta because of the definition of radian. Something you never want to lose track of because it saves you a whole lot of confusion. You see certain things. Okay. So the total thing. Okay. Another thing that I meant to Paul. Here is. You got a K vector from that sort of right? This is times K and this is times K. So I left my K vector off. And there's so rather define K prime that's in the negative 70 centimeters forever. Here. Centimeters forever. 10 to the negative 7 is easy to remember. You know, it's just 2 pi times. Okay. Then I'll talk about permittivity of free space and various materials. Probably next time, maybe not next week. Okay, well, anyhow, if you sum this up. Get this, and the sum of all your delta thetas is just 2 pi. This equals this. Only difference between this and this is 2 pi. Okay. All right, well. I was originally just going to do this. Now, I want to quickly dispose of the infinite field of infinite line. Now, infinite line charge on the x-axis, okay? And I want to take a point P off here. I want to take a typical increment here. And an increment over here. And I'm going to choose these 2 increments so that they lie at equal distances from P. Okay. So this will be a delta. T sub I. With T sub I star. Without loss of generality, I'm going to put P on the y-axis. You have an infinite line of charge. You put the y-axis any place on that infinite line of charge, and you have an infinite line of charge to the right, not charge, an infinite current. An infinite current to the right and an infinite current to the left. So the y-axis would be any point. So this is going to be this is going to be the field for any point at all. Okay. This semi-rigorous way to indicate the scene. And so it's pretty simple. Here we have an R vector. Let's say that this is at distance. Okay. Here. We'll call this RJ and call this RI, just for this solution. And kind of implicitly, your TIs, your I's are positive, and your I's this way go next. It's some negative infinity. Okay, so RJ star equals negative RI. If the current is to the right, then we have this field out of the currents to the right. Again, the field is out of the board. Is that out of the board? Okay. So the field turns out that K prime times this, the I equals K prime pi delta T J star plus RJ star over R squared. R is just equal to Raise square closure. Double TI. And, you know, it probably would have been better off using delta axis because it is on the X axis. But I had T in my head. So we can use anything we want for the parameter. At any point, you say, okay, let's let our TIs be even X lines. What it comes down to then is well, negative 2 times the actually, I don't need to. So you're going to end up integrating this cross product. Once I'm after this, the direction of the field is always out this way. But you have that sine theta thing because of the cross product. So now I'm gonna throw in the theta of J. Theta of I here, and a theta of J here, I'm kind of skipping steps. Because we're 2 minutes over time. What's theta of J? The sine of theta of J is just A over the square root of A squared plus J squared. Okay. Which is going to give you 3/2. This thing is squared. This is going to give you another square root of A squared plus TJ star, which is going to give you a 3/2 power of this thing. Okay. And then you got to integrate it from negative infinity. I'm pretty sure. Look through it just. Just review through your assignment, pretty sure they run you through that, it's done in your text. So didn't have time to do it well, I'll let you go, but there's the geometry of it. See how they parameterize, if they're gonna use axis instead, it's easy.